Still good morning and Assalamualaikum warahmatullahi wabarakatuh to everybody. Um, well, you know that it has been explained about zeolite previously, which was very interesting for us to know that the framework flexibility influenced the probably synthesis strategy. But today I'm going to talk about in terms of the experimentally point of view. So hopefully most of you knows about zeolite. This is the crystal shape of zeolite. So it shows coffin type morphology, what's called coffin type morphology, and we could see that the inside these crystals. So in the molecular point of view, so the zeolite normally contain strong acidity. So the Bronsted acid sites and the Lewis acid site are present within the framework of zeolite. This is why zeolite has been used mainly in industrial as a catalyst, for instance. And due to this, the channels, crystallinity, and then the micropore framework. So the high surface area is also very high. Is used as catalyst. So yeah, if we calculate the 1 gram of zeolite, and then knows that the pore length is about this order of magnitude, and then we correlate the, we just stack the pore until this long, and probably we could have this distance between Earth to Mars. So in the same order of magnitude. So this is showing the excellency of zeolite in this respect. Okay, has been used as the most widely catalyst in industry. So particularly in the catalytic processes. So you know that the this is the just the background of chemical industry processes, and then you see that the catalytic processes plays major roles in the chemical industry, and if we break down again, we saw that the heterogeneous catalyst plays much a role in the industry. So this is where zeolite plays around. So of course, in terms of the catalyst sales, the zeolite normally used as a refinery catalyst. So it has an equal share with all of the other global catalyst markets. So I think zeolite is one of the most important catalysts in the world. Of course, this is due to the shape selectivity of zeolite. If you know already that for instance, in the removal of wax, the zeolite can smartly identify the linear alkanes compared to the branch. So it's helped us to improve the cold flow properties in order to get lubricating oil. And also there is also a function as a product diffusion control. So the more the molecules that has a shape close to the dimension of the pore in the zeolite, they can diffuse faster than the other molecules. For instance, in the production of paraxylene as the intermediate of the styrene, if I'm not wrong. And also there is a restricted transition state that is a characteristic also in the zeolite, that it will not form such bulky products. Instead it will form such a desired selective product, industrial product. So, of course, in the refinery process in the industry, most of them in the petroleum industry, the fluid catalytic cracking is using zeolite. So in this process, for instance, in order to get more valuable chemicals like gasolines and probably other fuels, so zeolite is used. So as a catalyst, as an FCC catalyst, fluid catalytic cracking catalyst, there are structures of catalysts. Not only zeolite is used in the materials. The other materials like matrix, it contains amorphous alumina. This is used due to the large porosity. Also, it has some active sites, acidity, for instance, to control the catalysis reaction, the catalytic reaction. Also there are binders and also fillers. These materials normally used as to strengthen the physical strength of the catalyst in the industry. And zeolite is micropore materials, but of course to carry out this industrial catalytic reaction, we need other than micropore. So that's why we also try to involve the matrix, so it contributes the mesoporosity in this process. But in fact, the zeolite could not contribute until this far. So actually, this is the motivation for us to synthesize zeolite with the hierarchical porosity, containing probably extra porosity, such as mesoporosity or probably macroporosity. So if you see that there is trade-off performance actually, if we look at the zeolite and the mesoporous materials, for instance MCM41s. So this is the desired processes. The zeolite has a strong acid side, but MCM41 has a weak acid side, for instance, like that. And then in the other processes, zeolite is probably is not favorable. So it has a low formation of diesels. So also probably due to the relatively small microporosity, so it has a diffusion limitation in that respect. So probably this trade-off performance can be solved in the new hierarchically porous zeolite. That's what we call. Of course, we could synthesize to solve these problems. I mean, to increase large surface, to increase the surface area, and then to get some other degree of porosity, we could also synthesize nano-sized zeolite, or we could synthesize probably wide pore zeolite, which is unusual. But this is still a big problem for the zeolite synthesis. Dr. Azel proposed some framework flexibility, because we still don't understand what's going on during the synthesis of zeolite. That's why it's difficult for us to synthesize bigger wide pore zeolite. So the realistic approach to get this hierarchical zeolite is probably to introduce the porosity within the crystal morphology. So in order to do that, so this is what we want actually. So we just somewhat destroy some of the external surface of the zeolite crystals in order to get the mesoporosity, for instance. The mesoporosity is scaled around 2 nanometers to 50 nanometers. So the micropore is less than 1 nanometers, for instance, or maybe less than 2 nanometers according to the IUPAC. And for instance, this is MFI zeolite. It has 0.5 nanometers, which is in the same dimension as the desired industrial molecule. So how do we do that? How we can synthesize those zeolites? So this is from literature. So they were using hard templating routes, to synthesize hierarchically porous zeolite. So they started from the silica nanoparticles with the monodispersed silica nanoparticles, and they somewhat introduced carbons in order to get replica of these silica nanoparticles. So the silica was removed, and then within this hole, they try to use this as a reactor to synthesize zeolite. So this is the zeolite, probably ZSM5, one of the most famous zeolite type structure, was synthesized in these so-called carbon reactors. And then they remove the carbon, they can get the zeolite in monodispersed size. And also the hierarchical porosity can be obtained through the interparticle space. Of course, there is a soft templating route which started from the bottom up, and then using the precursors, and then started to get the zeolite with the hierarchical porosity. We were using the surfactants assistance. So surfactant will self-assembly, cooperative self-assembly in the nuclei of zeolite. So forming such a micelle. And this cationic surfactant normally forming such a micelle, and then they can make such a hole, a mesopore hole in the nuclei of zeolite, or probably the crystal of zeolite in the end. So then when we remove this micelle, we could get such a by calcination. By calcination, we could get at high temperatures, we could get the mesopore within the crystal zeolite. So this is one of the approach to synthesize reticle porous zeolite. And other approach also has been done by researchers in the world, like such as a top-down approach. So they just they silicate or they aluminate the external surface of the zeolite crystal, and then but this is probably this approach is not well controlled, because you can destroy the whole crystal, in fact, in the end, if you don't control it beautifully. And of course, this is the MCM22 can be remove some of the lamellar part, and the structure in the end collapse. So this is one of the disadvantages of using the top-down approach. So we were interested to synthesize with this bottom-up approach with the surfactant templating route. And but the problem is using this surfactant templating route, we could get such a physical mixture in the end. We are expecting to get this zeolite with hierarchical porosity in one system, I mean in one crystal morphology, but in the end, if we are not careful, if we are careless, we could get two materials, somewhat mixing the mesoporous materials with the mesoporosity and the normal zeolite. So this is the disadvantages of this surfactant templating route. So in order to direct into these directions, so we are using such a modified surfactants. So this modified surfactant is to add some alkoxysilyl group. They can hydrolyze into the network of silica network, which is then crystallized into zeolite. So that means we have to stick the micelle formation and the zeolite nucleation crystallization. This is the idea. So if we do that, we hope that we get these materials. If we don't do that, we just took the normal surfactants. So probably the nucleation will go separately into these physical mixtures materials. And of course, there are many literatures reporting about the using of the modified surfactant, so-called modified surfactant with the alkoxysilyl group, the hydrolyzable group, from the cationic group into the somewhat the polymer and non-ionics, and then they can get many kind of zeolites. But we were interested to get the siliceous zeolite, so that has the if you see that the silicate one, the MFI type morphology zeolite, it has a neutral framework because it doesn't contain any aluminum, so there is no negatively charged framework that can be compensated by some cations. So this is neutral framework. It's called silicate one, and we would like to synthesize this silicate one with hierarchical porosity. So if we are using the cationic type of modified surfactants, probably it will not work because the electrostatic interaction will influence the nucleations, and because this is neutral framework, so we hypothesized that we were using the non-ionic type of modified surfactants. And you can see that we successfully synthesized this MFI zeolite, which is silicate one, the neutral siliceous framework. So the high angle XRD show the typical the pattern of MFI zeolite. And we also look at the low angle of XRD. It shows it doesn't seems to have the structures of the mesoporosity, but it's just like a probably wormhole mesoporosity from this. And we compare between the mesoporous silicate one that we have and the mesoporous ZSM5 using non-ionic type modified surfactants. So we could see that the non-ionic type modified surfactant is suitable for synthesizing mesoporous silicate one because it has narrower border size distribution compared to the ZSM5. So we conclude that our approach using the non-ionic modified surfactant is very suitable for synthesizing the neutral siliceous framework. You can see the morphology. It doesn't seem to show the normal morphology because the normal morphology would have a clean surface, and this is probably like a durian fruit. And probably, I don't know why Southeast Asian people love this durian fruit so much compared to European, because it's smelly, of course. You can find it in Singapore or in Indonesia, Malaysia, about this durian. But I'm not sure if you like it. And it's all over the place, so we have this kind of morphology all over the place, confirming that we have only one type of morphology, suggesting that the zeolite crystal with theoretical porosity in one system, not a physical mixture. That's good news. We also characterize this crystal we're using the transmission electron microscope, and we could see some lattice fringes, so confirming that there is a despacing of zeolite here. And the pore size distribution seems to agree with the one that we have a nice better picture of this showing the probably 2 nanometers mesopore size. Yeah, why we synthesize silicate 1, because silicate 1, even though there is no acidity or probably mild acidity coming from the silanol groups, and this is very useful for the production of caprolactam. So it has been commercialized in Sumitomo in Japan, from a long time ago. Yes, next is me and my students try to incorporate just the surfactants. So to make this modified surfactant is quite tricky, because we need to synthesize, to modify in the laboratory first, because there's no commercial available the modified surfactants for sales. So this is we try to avoid this if possible. Yes, but when we just implement, like I said before, that if we utilize the normal surfactant like CTAB, it will form such a physical mixture. This is what we avoid. But we try to implement the non-symmetric surfactant. We were thinking that the symmetricity of the surfactant probably could help the the nucleation of mesoporous materials preferable. We try to find such a surfactant molecule which is not symmetric, and it's hard to make a mesoporous materials. So we implement this into the zeolite recipe, including the use of the template, what you call the structure directing agents in the case of MFI zeolite. So we try this. Well, we could get such different morphology. So when you increase the concentration of surfactants, so from this to here, so in the middle of the concentrations, you would get such a different morphology compared to the low concentration and high concentration of surfactants. And this morphology is believed to have a hierarchical porosity compared to this one. Yes, indeed, from the nitrogen absorption experiment, we see that the middle concentration of surfactant has a type 4 isotherms, showing that the capillary condensation forming the mesoporosity. You could see the BGH pore size distribution showing the narrow pore mesopore distributions. But when you use low concentration or probably too high concentration of surfactant, this will not form such a narrow distribution. This is due to it doesn't reach the critical micelle concentration, critical micelle concentration during the synthesis. Yes, we could develop other technique, but this is unpublished. I don't want to show you the recipe. Especially this was synthesized in the absence of template, but in the presence of surfactant, of course, because we were talking about surfactants. And we could get the hollow MFI morphology, a hollow spherical morphology, that is very unusual, and probably it would be good for making a complete hierarchical porosity of zeolite, containing macroporosity, mesoporosity, and of course the microporosity in zeolite. Yes, do I still have time? Of course. Yes, I show you already the use of surfactant template include, on the left side, and of course there are many good researchers out there, and we could learn from them, and then they could synthesize the hierarchical porous zeolite by using only single organic molecule. So this organic molecule is the long chain of surfactants but containing some, structure directing agent or zeolite. They're connected within one molecule. And it's very interesting, and we try to reproduce the experiments from the Journal of Nature, and yeah, we could reproduce somewhat. That's good news, because repeating the Journal of Nature is not easy. And well, we could get almost similar morphology compared to the literatures, and we could also see that the the lattice fringes. This is the so-called unit cell framework of the zeolites. You could see this. This was done by Sumitomo Chemicals. We had collaboration before, but by having this nanosheet, very thin morphology of zeolite, when we remove the organics from the framework, so the some of the structure collapse. Yeah, so this is the disadvantages of having a very thin nanosheet. So that's why we don't want nanosheet. So we want bigger. But still probably in the in the scale of nano, but not 5 nanometers, probably 50 or maybe 100 maybe nanometers. Yeah. Okay. We try to to find new organic SDA. We look at the channel, channel within the MFI zeolite, for instance. So if you look this top view, you can put balloon. This was taken from the Denmark University. So you can put the balloon in the unit cell of the MFI framework. You can have a straight channel and a sinusoidal channel. This is typical characteristic of the pore in the MFI zeolite. And if we look this channel into this image, the side view. So actually this channel was developed by sort of organic molecules. That's what we call structure directing agent. So normally MFI zeolite was constructed by only single ammonium ions here with the tetrapropyl ammonium ions. But if we can have diammonium, in fact. But we have to negotiate with the chains, space between the two ammonium ions. If you have 7 carbon chains, so probably it's 9.8 angstrom. Yeah, probably it will fit into this, into this channel. Yeah. If you decrease into 8.4 angstroms, probably I don't know if it's work, but you can decrease again up to down to 5 carbon channel. When we learned from the Nature paper, because they were using very long surfactants, about 22 carbon chains. So it's too much. That's why they can make nanosheet. So only just some part of the carbon can mediate the formation of framework of zeolite. But we were thinking the other way around. We just want to use as small as possible the structure directing agent, the organic molecules. So this is what we are using. So we were using just C5 space between the diammoniums, and probably it will not fit very well in the channel. So it will not go into the second intersections. So probably stop in here. That's what we expect. We just want to inhibit the crystallization of the zeolite. So in order to get defect size, more mesoporosity, something like that. Okay, we have successfully synthesized the zeolite according to the XRD patterns. And the morphology looks very, strange. Yeah. We could get such a nanosheet plate like this. Yeah, probably this is 15 nanometers, not as small as the Indonesia paper that can collapse. So, but since the MFI zeolite is known to have a 90-degree rotational intergrowth, so it also has a 90-degree 90-degree rotational intergrowth of the crystals. So it formed a lot of 90-degree rotational intergrowth, even in this side also. So actually we are making the macroporosity in here. We look at, I was lucky that this is a photogenic zeolite. So I can make SEM from this side, and I can make SEM from also the top side. So this was lucky, and we published also in quite a good journal. And we look at transmission electron microscope. We could confirm that where is the straight channel, where is the sinus channels over there by identifying these axes. And yes, it has porosity within the nano sheet, not 2 nano sheet crystals, about 2 nanometers from these pore size distributions. And from this, macroporosity, you could see it by visually, macroporosity is there. Yeah, so we have a complete hierarchical porosity of zeolite in the end. Macroporosity, mesoporosity, and of course the microporosity within the zeolite. Yes, we could apply to the ZSM5 case. Before it was silicate 1, we could apply the same. So we could hope probably this can be used as a catalyst in the industrial, in the acid catalytic reactions. And yes, this is to confirm that the aluminum is substituted in the framework. This shows tetrahedral formation of aluminum by a solid state NMR. And this is again the mesopore size of the ZSM5 that we produced before it was silicate 1. And we tried also to understand the mechanisms this working from the nano particle formations, and then they can make thin plate, and then suddenly the 90-degree rotational intergrowth occur. And it also influenced by the temperatures applied during the synthesis of zeolite. We could understand the evolution of this morphology, but with the note with some conditions, 175 degrees Celsius will not make such a high degree of rotational intergrowth, because the organic the ammonium has been decomposed into some new species by observing from the solid state NMR, carbon NMR. And we could also minimize the crystal size of this, U4 shape, or whatever you call, the ghost shape or something like that. So we could also minimize the crystal size of this so-called nanosheet morphology, but this is not published, but I don't know when it will be published. In summary, so I hope I convinced you, show the several rational strategies to synthesize hierarchically porous MA5, particularly MA5 zeolite, ZSM5 and silicate 1 by surfactant templating route, or probably the use of non-ideal structure of organic structure wrapping agents to drastically alter crystal morphology. So I'd like to thank my postdoc advisor, Professor Kubo and Professor Simojima, and also my colleague, Dr. Wacharov, and also this is my collaborators, our collaborators, Dr. Tatsuya Suzuki from Sumitomo, and also my colleague, Mr. Suzuki, and also my students who has done a lot of good work in ITB that I presented today. Thank you very much. Also fun.
Sure, we can have a couple of questions. Young lady there. Yes, that's
in surfactant and taking route, is there any special, I would like to ask you about, is there any special requirement or criteria for us to choose or to modify the right surfactant to get the right structure or form?
Yeah, so the question is about to use the surfactant to direct the structure. But in fact, this surfactant can only direct the formation of pore, mesopore. So it's not the structure of zeolite. Yeah, so apparently like that. So of course the mesopore can have a structure like hexagonal, cubic, or lamellar. So yeah, it depends on the dimension, the chain surfactants. Of course, yeah. The longer the chain, probably it will form lamellar type, or there is some compromise in that. Yeah.
Second chance. I'm really interested in your hierarchy courses, like here. In the top side, there are macropores, and inside is micropores. You're introducing surfactant containing bulky, I can say. My question is, this surfactant can control the top side and inner side, or the inner side will be make a microprotein itself, or like one. So we have two pore sides.
You mean the last morphology that shows the U4 shape or something like that? Which one? The durian shape?
No. I mean, you're introducing the surfactant containing.
But not in the last morphology. We didn't use surfactant at all. It was only just the ammonium organic template. Yeah. but only in the first presentation I showed that the surfactant was used to form the durian shape. Yeah.
Meaning the control the inner micropores.
It was controlled by the ammonium organic.
Oh,
Not the surfactant. Surfactant has a hydrophobic chain law. This is not surfactant. Yeah, not amphiphilic molecule. Okay.
Oh, sorry. I'm looking at all the students at the moment.
I have several questions. We can talk about them later. Yeah. One question. Once you make the mesopore with using the surfactants, can you use that crystallite and seed indusialite with the micropore? Sorry, it's a little speculative.
You mean to get the same morphology? To use the seed of that? That's a good question. We haven't done it for sure. We haven't done it because yes. I don't know. It's very interesting to see if the crystal can repeat, you know, and as a seed can repeat again the formation of the same morphology. That would be very good. I don't know. Thank you. It's worth to try and publish in Nature with you. Yeah, sure. I will appreciate your idea. Keep it safe.
Okay, well, we can have some more questions at lunch, so let's take